Are we alone in space or not? With the current level of knowledge about space and biology, the answers will be speculative. Despite this, a scientist is more likely to say no, because science basically looks at all processes systematically and is guided by a probabilistic approach. Let's look at it. So, 4 billion years ago, the first replicator appeared on Earth, a molecule similar to ribonucleic acid in the cells of our body. The main characteristic of life is self-copying. The replicator molecule is both a matrix and a printing press, which produces its copies from available chemical elements. With the advent of the replicator, there was the potential to create not only cells, but also their clusters, and from there multicellular organisms, like you and me. The question of the appearance of a replicator is interesting in itself, but we are now interested in how common its occurrence is on planetary systems. The probability of an accidental occurrence of a replicator just like that, out of nothing, is non-zero. According to the calculations of astrophysicists, there are more than 100 billion habitable planets in the universe. There is a fact that life has already originated on Earth. That is, a replicator did appear on one of these planets. Well, it can't be that life didn't appear on such a huge number of planets, too. And if you still don't, then the probability of life would be 1 in 100 billion, and that would be enough to settle down. But this is a very superficial answer. In addition, we cannot land on each of these planets and carefully study its surface in search of replicators, and we have already realized that the presence of a replicator means the presence of life. What if the appearance of a replicator is typical, but its survival and gradual evolution into multicellular organisms are not? Armed with knowledge from chemistry and astrophysics, let's ask a simple question. What is it in our solar system and our planet that contributed to the development of the replicator into multicellular organisms? A necessary condition for organic life is carbon. It allows molecules to bond with each other and form diverse shapes. Among the chemical elements known to us, only silicon has similar properties. That is, in order for life to originate on the planet, carbon or silicon must be present there. Other necessary conditions are the presence of nucleotides and proteins. For nucleotides are necessary for the formation of DNA, which underlies the existence of any cell. They also produce proteins, the building block of these very cells. We don't know exactly how they originated. Moreover, it is not known which arose first, proteins or nucleotides, because both components were necessary to create self-replicating life. In addition, at first there were no suitable conditions on Earth for the existence of life in principle. There was no oxygen, but there was water. Because only complex chemical compounds could be formed in water, oxygen appeared with the emergence of cyanobacteria and photosynthesis. The energy of the sun was transformed into oxygen through bacterial secretions, no matter how unpleasant it may sound. The process of oxygen saturation of the Earth took place for many millions of years before life could reach the next stage, multicellularity. Paleontologists distinguish the so-called Cambrian explosion, when in a certain geological layer, namely 600 million years ago, scientists began to find the precursors of all those species that we know now. It is quite possible that the explosion was not an explosion, but simply shelled and vertebrates appeared in the Cambrian. Invertebrate life was no less diverse, but there was nothing left of it in the rocks. But it's not even that's interesting, but the fact that more time has passed from the origin of the replicator, about 3 billion years, to the emergence of primitive vertebrates than from the natives of the Cambrian to you and me. In other words, the creation and cultivation of multicellular life in all its diversity has been a long process for evolution. And what is interesting is that during this time, the state of the Earth as a space object remained stable enough to support the development of life. Of course, there were extinctions, for example, the Great Permian 250 million years ago or the extinction of the dinosaurs 65 million years ago. But life was always able to recover from these blows of nature. Species have already managed to gain a foothold on the planet in great diversity, and the mechanism of gene transfer at the DNA level and ribonucleic acid has been perfected. What allowed life to stabilize in terms of cosmic forces? If earlier, in 1960, astrophysicists considered the Sun and our system typical of the universe, now the general opinion has changed. The Earth has helpers protecting it. Our first helper is the Moon. Our satellite stabilizes the position of the Earth's axis of rotation in relation to the galaxy, which is why the Earth does not tumble around the Sun as much as other planets with a similar mass. The second helper is Jupiter. The largest planet in the solar system also has the largest mass, due to which it attracts any debris that flies from the depths of space. Without it, the Earth would be in much greater danger of being bombed by meteorites. But the most interesting thing relates to our main benefactor, the Sun, or rather, the period when it arose. As you know, solar systems arise from gas clouds when they gain sufficient density. But in our case, the explosion of a neighboring supernova helped. He accelerated the formation of planets. Our solar system, in turn, circles around the core of the Milky Way galaxy, entering and leaving the so-called arms. Entering the spiral arms greatly increases the risk of encountering a supernova explosion, as happened when the Sun had not even appeared. For a formed planetary system, such a collision would certainly be a disaster. Stars and the beginnings of planets form inside the sleeve, and the planets themselves form outside it. If the solar system, after its origin, turned close to the galactic core, it would often cross the arms. Explosions would not allow life to arise and develop. If the Sun had moved in the center of the arm, along the so-called corrotation circle, it would have delayed the collision with the supernova, but it would have happened sooner or later anyway. If the Sun were far from the core and rarely crossed the arms, it would not form planets. We know that after the formation of the Earth for 4 billion years, no explosion disturbed life. In other words, the Sun has been outside the arm and the disastrous effects of the stars all this time. This happened because the circumference of our system's motion intersects the arms at an angle. That is, the transit time of the orbit inside the sleeve is significantly less than the time outside it. If the gas cloud has been inside the sleeve for 300 million years, then the Sun has been outside it for 4.5 billion years. Our system, as a lucky player, moved away from roulette in time to nurture and cultivate its winnings. And how many planetary systems were destroyed at the stage of the gas cloud or before they had time to form properly? Probably a lot. Viewed from this perspective, life should be a phenomenon of the rarest order, whereas total destruction is the norm. All these necessary conditions, both chemical and cosmic, led to the emergence of life as we know it today. We don't have documentary evidence of life anywhere else, so we can build on our own precedent. Some variables may be different. We have already mentioned carbon and silicon as the foundations of life, but the disappearance of any of these variables would most likely have stopped life. As Stanislav Lem aptly wrote, we arose after going through a lot of needle ears. Surprisingly, at none of these stages did a global catastrophe occur and the complete destruction of our system or life on the planet. To summarize what has been said, it is difficult to give an accurate estimate of the number of habitable planets in the universe. Surely the ratio is more than 1 in 100 billion, as we said at the beginning. Given the above, life, especially intelligent life, one that would enjoy the relative stability of existence for billions of years and not be shaken by any catastrophe, such a life should be very rare. And that is why our civilization today has a great responsibility for its future. We have nowhere to look for a guide. The dark cosmos is silent and lives according to the cold laws of the birth and death of stars.